In the last class we had seen that what is the value of n for which the propellant will operate stably, right. In all the analysis that we had looked at till the last class, we had looked at basically determining the burn rate in a strand burner or a Crawford bomb, right. Now rocket motor, depending on its application, if it is in a tactical missile or a launch vehicle, can be very large compared to what you do in a strand burner, right. Strand burner, you essentially take a few grams of propellant and measure the burn rate. Now in today's class, let us look at what are the parameters that are going to change when we go from this small strand burner test to the actual motor, and how do we account for it in some sense. Okay. Firstly, if you remember, I had written that burn rate R dot is a function of chamber pressure, initial temperature, cross flow velocity and composition. This part of about cross flow velocity, we are going to look at it in a little more detail. This is going to cause what is known as erosive burning. That is, if you have a rocket motor whose port diameter is quite close to the throat diameter, then it is going to be subjected to erosive burning. We will discuss that a little later in the course. So this is one part we will not be able to measure in our strand burner tests. Okay. So the first thing that we are not able to look at in a strand burner test is erosive burning. Okay. That is going to be different in an actual motor compared to this. There are some small motors which are spun at some high RPM in order to make them go straight. Okay. These are probably in tactical applications only, tactical missiles only. They are spun at a high rate so that they go straight. Now what happens in such a case, especially in an aluminized propellant, is these aluminum particles are subjected to a centrifugal force, so they tend to burn much closer to the surface. So therefore the burn rate increases. Strand burner, you do not have that, so that is something that you have to account for. Okay. Then what are the other things that you think will change from the small strand burner to the actual motor? Chamber pressure, you can essentially hold it the same as the what is going to be there in the large rocket motor. That is not something that is bound to change. Yes, G loads, but that is not going to be large in both strategic missiles and launch vehicles, because if you look at it, their accelerations go from somewhere around 1.6 to 4 Gs. They could be of significance in tactical missiles. These come on because they are subjected to enormous accelerations, right. Then as a consequence of this, and also if you look at the entire missile or launch vehicle, it is a large mass of propellant, right. There are regions which are subjected to strain because of its own weight. Those things not been kind of included in our tests in the Crawford bomb, right. So effect of right. So these are the things that change from our Crawford bomb test to the actual test. Typically it is seen that the burn rate variation from a Crawford bomb test to an actual test is somewhere around less than 10%, somewhere around 7 to 8%. Okay. It is still vital, primarily because if you look at the GSLV kind of configuration or the Ariane 5 kind of configuration or the space shuttle configuration, you have two large solid rocket motors, right. Now if they do not complete combustion at the same time, you are going to have a tremendous side force which could topple the entire vehicle, okay, which is something that is not desirable, or you need to have a tremendous control force to overcome this, which is also not easy to overcome, because the thrust produced by this motors are very, very large. Okay. So that is something that is very important to note, that there are changes to burn rate from the stand test, Crawford bomb test, or the strand burner test to the actual motor, and there are kind of thumb rules to tell us what is this difference going to be. People with experience will know that if they conduct the burn rate in a Crawford bomb, and then as an intermediate you have something known as a ballistic evaluation motor, and then the actual motor. So if you have the data for all these three, then depending on the Crawford bomb tests, you can then what they do is, while making the propellant, they take a portion of the slurry and get the burn rate of the slurry, and if the burn rate is different, then they add the suitable burn rate modifiers to get it back to the level that they want it to be, so that they know what is a priori before they cast what is the burn rate, right. As I said, in some tactical missile applications, if you want it to go straight, they are spin stabilized. You know, bullet is spun at tremendous rate so as to make it go straight, otherwise aerodynamic loads will make it go in a different direction, right. So you want it to go straight, then you need to spin it.
How the aerodynamics loads are avoided by spinning?
It is called as gyroscopic stabilization. That is, if you still spin at some very high rates, the shells are spun at something like 18,000 rpm. Okay, if you spin it at that rate, this is like a cycle wheel. As long as you are pedaling it, you won't fall off, right. Even if there is a force that tends to destabilize you, right. If you look at the cycle, it is like an inverted pendulum. You can model it as an inverted pendulum. It is a mass that is there at some height, right, and inverted pendulum is, you know, is very unstable. Small disturbance can make it change its stability. So there what you do is you spin the wheel so that you get that stability. Unless you are moving forward, you cannot stabilize yourself, right. So in the same way, if you spin it, you can then make it go straight. And coming back to the topic, we had also looked at certain equations for pressure in the last class, right. We had said that the chamber pressure Pc is given by fine. Now we can also add thrust, define thrust in a similar manner, right. We can use thrust, we knew was F is equal to Cf PC AT, right. So now if you use this definition for PC here, you will get F is equal to Cf rho P okay. So this sorry, this has to be AT is, this is plus 1. This has to be minus, okay, because this is in the denominator. So which you can simplify as okay. So F you can define it in this fashion, right. We also know that A, the term A has embedded in it the temperature sensitivity part, right. So we can use that. We knew that A was A naught into exponential of okay. So if we plug that into this equation and this equation, we will get the variation of chamber pressure and thrust. Why are we doing all this? Let us try and estimate if there is a marginal change to, let us say, the burning surface area or the throat area or changes in temperature, what is going to be the effect on thrust and chamber pressure. Okay. Why is this important? First, thrust part I kind of explained it. In a sense, if you are looking at the launch vehicle part, you do not want the thrust to be different in the two motors, that is JSLV class of motors. Even otherwise, the entire launch vehicle, if you take a look at it, it should take the satellite to the required orbit height and it should give it the required velocity. If there is a shortfall, in some cases they do use some liquid engines to take care of that. Okay. But if you are looking at a missile, then again you have this problem that even though temperatures are varying widely, you still want to be able to hit a particular target, right. So you need the thrust to be estimated appropriately. Then if you look at the chamber pressure part, the if you look at all aerospace systems, the factor of safety is going to be very small, right. It is somewhere around 1.6 to 2.2. So, if your factor of safety is very small, then your margins are also very, very small, right. Due to changes in temperature, if the pressure exceeds by a large fraction, then you could have the motor bursting out, right. You would not want that to happen. So, we need to have some estimate of what is going to be the change to pressure and thrust if there are small changes to burning surface area, throat area and temperature. Okay. So, that is the reason we are trying to plug in all this into this equation. So, if you plug in the A variation also, you will get P c into exponential of okay, and similarly f will also have you can expand A in terms of this. So, f will be okay. So, we have included all the variations of AB, AT and initial temperature, right. So, let us now do something known as an incremental analysis, wherein we will see if there are small changes to the either AB, AT or initial temperature, what will be the corresponding change in terms of chamber pressure and thrust. How do you do this? Very simple, take a partial derivative, right. If you are looking for burning surface area, take a partial derivative of chamber pressure or thrust with respect to the burning surface area. So, let us do that. F and P c with respect to A B, A T and initial temperature. Okay. So, what is the with respect to, let us take firstly A B, what is the variation of A B with respect to, or what is the variation of P c with respect to A B. So, we get dou P c by, if I take P c, if I divide it by P c, this is the same as A B appears in the same fashion in both these equations, right. So, the partial derivatives will be the same. If I take the partial derivative and divide it by the actual value, then I will get the incremental change. So, this will be the same as dou f by f is equal to here 1 by 1 minus n into Okay. And if you look at AT, again AT appears in the denominator here, and it has a different sign, different power here. So this is with respect to AB. Then for AT, these two will not be the same. So here AT is in the denominator, so it will have a negative sign. And lastly, if we look at how these two change with initial temperature, okay, I'll call TIN minus TIN naught as delta TIN. Okay. Then both of them change in the same fashion. If you look at this, both of them are raised to the exponential of this value. So both of them will change in the same fashion. So you will get okay. So we've been able to look at what is the incremental change to chamber pressure and thrust in terms of changes to burning surface area, throat area, and temperature. Now let us look at how each one of these will vary. If you look at burning surface area, right, burning surface area is the area that is seen by the flame. Now if you look at a rocket motor, this propellant can be extruded or cast. Okay. Either process you will have some kind of imperfections, that is you will have somewhere cracks, blowholes, right. So now if the flame comes to this position, right, let us say the position is somewhere here, or if it is somewhere here, it sees an additional surface area, right. Suddenly an additional surface area is exposed to the flame. Okay. So the burning surface area changes because of imperfections in the manufacturing process. These could be propellants are made in one place and then moved to another place to the launch pad, right. So, during the transportation it could the damage could be accentuated, that is, it could be increased. And also if you are looking at higher stages having a solid rocket motor, due to the enormous vibrational loads that come on the propellant while the first stage is burning, let us say, then these imperfections could also be increased there. Okay. So, we now know how burning surface area will change. How do you think the throat area will change due to erosion of the nozzle? You could also have deposit. Okay. If it is a heavily aluminized propellant, in some cases it is seen to have a deposition also. Okay. So, either case is possible, erosion of throat and as well as deposition. Basically in most cases it is erosion is the more predominant phenomena. Okay. Typically this throat erosion or deposition is a function of the burn time. If you have a large burn time, right, then you could have something like 8 to 10% increase in the throat area. If the throat area increases, then the pressure will drop. Okay. And you are also in a sense reducing the area ratio for the supersonic portion, right. So, it hits you in two ways. One is drop in pressure, and then the ISP will change because of drop in pressure one, and then again because of the expansion ratio being changed. Okay. The burning surface area changes if if you are trying to make a large rocket motor, let us say of the class of GSLV Mark III, the first stage, which is a 200-ton propellant. Okay. As I said, it is very difficult to make propellants without imperfections, right. There will be some amount of blowholes, some amount of cracks, things. So, what they do is they do detailed non-destructive testing, that is they take ultrasound images of the propellant and study it and find out where the imperfections are, how large are these imperfections. Okay. So, which is what makes it very, very expensive, because if you have to do the entire rocket motor, test it, right, it takes a lot of effort and time, and you also need those kind of facilities to make once the entire rocket motor has been made. And the reason why in one sense they make a segmented grain is, let us say you are casting 200 motors in one go. If you make the entire motor and if you realize that the imperfections are only in certain portion, then you have to redo the entire 200 tons, right. So, it would be better if you can make it in smaller segments, so that you can take out the portion that is bad and then replace only that portion, right. But if you have also too many segments, then your reliability in some sense goes down, and you are also exposing it to in some sense combustion instabilities, because you will have some protrusions coming in because of the liner, and that is something that you would not also want. So, it is in a sense give and take between these two, right. Now lastly, how much does the temperature vary, the initial temperature. Initial temperature varies from place to place, and also daily variation and seasonal variation. Okay. Even in a single place, depending on the season, temperatures can vary, and depending on the time of the day, temperatures can vary. One good thing for us is most of the solid propellants are very bad conductors of heat. Okay. So, it takes them long time to really sense what is happening on the outside. So, typically it takes something like depending on the size of the web thickness, takes something like 24 to 72 hours to soak the propellant. That is, if the ambient temperature changes, let us say from 27 degrees to something like 0, and if it is there in that condition for a very long time only, will the entire propellant go to that temperature. Otherwise, you will have a gradient even in the propellant. Okay. So, now we have kind of got these equations. Let us linearize them in a, or let us take a small variation in AB. Okay. These are non-linear variations. Let us take a small variation in AB, linearize these equations and find out what is the change in pressure and thrust. Okay. So, if you do that, I have taken two cases wherein one has a small sigma, one has a large sigma. I will also take for each one of them what happens when n is small and when n is large. Okay. Just one important thing, if you look at the sign of these incremental changes, both changes to burning surface area and initial temperature have a positive sign. Okay. Whereas the changes with respect to throat area have a negative sign. Now, as I said, also we will take two cases for n being small, n being large. This is incremental change in burn rate and correspondingly incremental change in the burn time. We know that changes in pressure and burn rate are related. R dot is equal to APC to the power of n. So, we can use that to calculate this, and if you know the burn rate, you can also calculate the burn time. Now, if you notice this, as I said earlier, this sign of this will be different from the other two, right. So, all this is with minus sign, whereas all this is with plus sign. So, the changes in burn time will be the negative of the changes in burn rate, right. So, notice that the worst case would be if you have a large sigma and a large n, then your changes to chamber pressure with 10 degrees change in ambient pressure can be of the order of 26%, right, which is pretty significant, and thrust will also change by the same margin. Okay. So, in a sense it is very important to have propellants that have low n and low sigma p, right. But what do we do if we cannot have them, right? There is something that we want. Sometimes we are not in a position to be able to achieve that. Okay. So, what is the next best thing that we can do as an engineer? The only thing is try and control it in some fashion, right. As I said earlier, if you look at this, throat area is in a has a negative sign compared to the other changes, right. One way to look at it is, if you cannot have a propellant with low n and low sigma, if you look back, you will find that homogeneous propellants are always going to have higher n and higher sigma, right, compared to composite propellants. So, if you have such propellants which are mostly going to be used in tactical missiles, what do? You can look at this, and in some sense, if you can change the throat area depending on the condition, then you will be able to achieve or you will be able to minimize the changes in initial temperature, because this has a negative sign, and that is what is done in certain missile applications. You will have a plug So, if you have a plug like this, whose diameter changes from one end to another, that is, you use a cone, and if you are threading this in some fashion, then you can move it in or out depending on what is the requirement, right. So, you will be essentially changing the throat area to accommodate for changes in the initial temperature, right. The other way to overcome this is, let us say we are in a position to store these missiles in a controlled environment, okay. And as I said earlier, these are very poor conductors of heat. So, it will take them a long time to soak to the ambient temperature. So, if you can maintain some of these missiles in controlled environment, then and you are able to use it in the next couple of hours, let us say, then these effects will not take too much of a toll, right. So, one way is to have a best is to have a low n and low sigma p. If that is not possible, then have something wherein the throat area is changing. This cannot be a solution for a large missile application, primarily because this plug is exposed to high temperature gases, and if the burn time is very large, it will tend to burn itself out, which again will dramatically change things. You won't want that either. So these are applicable only for small tactical missiles with small burn times, okay, not for large boosters or missiles. And as I said, if you cannot do this either, then the only way is to store it at a controlled environment, store it in a controlled environment. These are not possible for very large rocket motors also. In large missiles, you cannot have them stored in a controlled environment and then be able to move it to the launch pad within a very short time. So what is done in such cases is you will have a small liquid rocket motor attached to the payload, which will make up for any loss in thrust, which you can cut off at any stage. Okay. So that is what is done in missile applications in order to overcome this problem. Those small liquid rocket motors are called as velocity termination packages. Okay. So if you do not have the required velocity at the end of it, that will make up for it by burning for a short time. Okay. So in the next class we will look at how to go about designing a grain of a solid rocket motor. Okay. What are the things that we need to keep in mind? How do we get the required thrust time curve if we know a propellant has certain burn rate and other things. Okay. So we will meet in the next class. Thank you.